afternoon and welcome back to elementary algebra. Oh my gosh, I named the wrong course. All right, so welcome back to elementary algebra. I'm your instructor, Amy Fuchsteiner, and we are going to be looking today at the sum and difference of cubes, a slightly different factoring pattern from the last section, but a factoring pattern nonetheless. All right, so to go over the factoring patterns for the sum and difference of cubes, a couple of things are important. First of all, there will be two terms in these particular polynomials. You're going to start with two terms. There's either going to be a sum, as in a plus sign between them, or there is going to be a subtraction sign for difference between the two terms. Both of those terms will have to be cubed. So the first term is cubed and the second term is cubed. And the pattern for the factoring goes like this. All right, so if we have an a cubed plus a b cubed, you want to find what a is, right? And then you want to add to it whatever b is. That means we will need to be familiar with cube roots. If you are not familiar with cube roots, I do have a listing of some of them down here below. So we'll be referencing that as we work through the problem set here. Once you have listed the cube root plus the cube root of b, so the cube root of whatever your first term is, plus the cube root of whatever the second term is, then it actually gets multiplied by a trinomial. And in that trinomial, you have three terms. The first term is whatever a is squared. The sign, the next sign is the opposite. This was a plus, this one will be a minus, right? Then it is the two terms multiplied together, minus ab. Do I need two? Minus a squared b plus. Nope. And then we will add whatever the b squared is. Okay. So it is always a plus b, so the cube root of the first term added to the cube root of the second term. And then we're going to multiply that by a trinomial, where it's always the first term squared minus the two terms multiplied together added to the second term squared. Okay. The signs, I have this acronym from my colleague, Jason. He always calls it SOAP. As in the first sign is the same. The second sign is opposite. And the third is always positive. That did not turn out. AB, not AB, AP. Okay, so if we have the difference of two terms, we're going to do the same basic pattern. We're going to find the difference of two cubes. Sorry, we're going to find the cube root of a cubed, which is a, and the cube root of b cubed, which is b. The sign between them is the same as the original binomial, so that's going to be a minus. Okay. Then we will multiply that by a trinomial, where the first term is the a squared. The sign is the opposite of whatever it was in the original, so that's going to be plus. We're then going to multiply the two roots together, so a times b. And then the last is an always positive square of the second term. Okay? Yeah. All right, so we start with cube root. Oops. Sign is the same as the binomial. Okay. So So we want the cube roots of each term, the sign between them is the same as whatever was in the original binomial. That gives us our first a plus b, a minus b. The second bit is the trinomial. Okay, and in the trinomial, we want the square of the first. Then we do the opposite sign from the original expression. And then we do the product of the cube roots. Then we need a positive sign. So then we do a sum. All right. And then we need the square of the second. Okay. And this is our basic pattern. This is the basic pattern for the sum of, or the sum of two cubes or the difference of two cubes. I don't know why I'm having trouble talking this afternoon, but I am. So it's the same for the sum of two cubes or the difference of two cubes. Either way. Let's try some. Can we? All right. Okay, so my first example is h cubed plus 27. This is 2. It could be the difference of two squares, except h to the third is not a square, and 27 is not a square number. So this is not going to be the difference of squares, aside from the fact that it's a sum and not a difference. But it is 2, so I had to consider that. What I want to look at now is it the sum of two cubes? I do have a plus, so it is a sum. H cubed is an h, right? H cubed is a cube. H cubed is h times h times h. So there is a cube there, cube root of which is h. 27 is a perfect cube. 27 is 3 times 3 times 3. So I do have a cube root here of 3. Now, to use my pattern, I start with the cube root h of the first term and the cube root 3 of the second term. The sign between them is the same as the sign or the operator in the original expression. Sign is maybe not the right word. Operator is probably better. So whatever that operation is in the original, okay? Then according to the pattern, I want to square that first term. So that'll be h squared. I want the opposite sign or the opposite operator that I already used. So that's a plus. So this is going to be a minus. Then I want the product of the two terms. So h times 3 is 3h. The last operator is always addition or always positive, if you would rather. And then I need the square of the second term. 3 squared is 9. Okay, that's it. I can check it if I want. I can do h times h squared, which is h cubed. H times a negative 3 is a negative 3h squared. H times 9 is 9h. 3 times h squared would be 3h squared minus 9h plus 27. And my hope is that a bunch of stuff cancels out. So let's take a look. If I have an h cubed, that should stay. Negative 3h plus 3h. Yep, they cancel out. Then I've got a plus 9 minus a 9. Yep, they'll cancel out. And I'm left with just h cubed plus 27, which was indeed what I started with up there. So my factoring pattern worked. All right, let's try a second one. Here I have y cubed minus 512. This is a difference, so I do have to consider difference of squares. But y cubed is not a perfect square, and 512 is not a perfect square. So difference of squares, the pattern we practiced last problem set, is not going to work here. I do notice that y cubed is a cube, y times y times y, and that 512 is a perfect cube of 8, so 8 times 8 times 8. Using my pattern, I begin with that y and the cube root of 512, which is 8. And my first factor is going to be the y and the 8. The operation between them will be the same as what we began with, minus. So this will be y minus 8. And then for my second factor, I want to use a trinomial where I have the square of the first term, so y squared. My operator is the opposite of what I previously used. So that was a minus 8. So this is going to be a plus. And I'm going to use the product of the two together. 8 times y is 8y. And then my last operator is always positive. Same, opposite, always positive. And I need the square of the 8, 64. Okay. Now, if I want to, I can check this. Y times y squared is y cubed. Y times 8y is 8y squared. Y times 64 is 64y. Minus 8 times y squared is a minus 8y squared. Minus 64y minus 512. Note that because we're careful about the signs, things do cancel out. And yes, we have y cubed minus 512, which is what we started with. This is a verification that the factors work. Okay? All right. So to try a couple more so that we go through a few and we have some ideas here. So I have 8g to the third minus 1. 8 is a perfect cube. G cubed is a perfect cube. This is 2g times a 2g times a 2g. 1 is also a perfect cube. It's 1 times 1 times 1. So to use the pattern, I want the root 2g, and I want the root here of 1. The sign would be the same as what was in the original. Now, my first term is going to be the square, or if you'd rather, if you're more visual about it, I've used this 2g. So now I need to multiply these guys together. So that's going to be a 4g squared. I want the product. I need the opposite operator, so I need a plus here. Then I need the product, so that's going to be 2g. And then I used a 1, 1, and then always positive, a square. So I have a 2g minus 1 times the trinomial 4g squared plus 2g minus 1. Oh, we haven't really talked about it yet. I got this far in without saying it. This trinomial never factors. I'm not attempting to factor that trinomial any further because when you use the sum or difference of cubes, the trinomial that you create is always not factorable. It's just the way it works out. So I could go in and prove it to you, or you can take my word on it. I'm really hoping you take my word on it. But it's never factorable, right? Okay, so next one is b to the 6th minus 125. It is a difference. Is it a difference of cubes or a difference of squares? Well, 125 is not a perfect square. Is 125 a perfect cube? Yes, it is 5 times 5 times 5. I know that one. Maybe you don't know that one. If you don't know that one, you can reference this list. See, 5 cubed, 125, right? Or you can use your cube root button on your calculator. If you do not have a regular calculator like this, I don't know if this will help you, but I'm going to put it in there anyway. The cube root button, hold on, I'm going to zoom in. Focus. Don't look if you've got vertigo. Don't look if you've got vertigo. It's not focusing. There we go. Okay. I don't have a cube root button, so to speak, but I do have See that chevron? See directly above it how it's got a little X and then a weird square root? So I'm going to do a 3 for cube root, second chevron. That is now putting that 3 in where that X is to find the cube root. And I'm going to do 125 because I want to know if 125 has a perfect cube root. And it does, it's 5. So that's how you tell. Once again, that is on mine above the chevron key. It's a little X and then the square root key, what looks like the square root. If you put the number in first and then the X. If you don't know how to find a cube root on your calculator, you can always use Google. All right. So I do know that b to the 6th is a perfect cube. It is b squared times b squared times b squared. 125 is 5 times 5 times 5. Using the difference of two cubes, this will be b squared minus 5. Remember, the first one is the same. The second one begins by squaring or by using what's left here. So that'll be b to the 4th, opposite operator, and then the two of them together, so 5b squared, and then square the last one, always positive. There you go. B squared minus 5 times b to the 4th plus 5b squared plus 25. All right, let's try x cubed plus 64y cubed. X cubed is indeed x times x times x. 64y cubed is 4y times a 4y times a 4y. I do know y cubed has a cube root of y. I do know that 64 has a cube root of 4. Using the pattern, this would be the root of the first, that's x, plus, because I want to keep it the same as the original expression, the root of the second, 4y, times a trinomial now, where I use the first one squared, or if you're more visual, what's left here. If I've used one of those x's, I have an x squared left. Now I need the opposite from what I started with. So I started with a positive. This is going to be a negative. Or I started with addition. That's going to be subtraction. The product of the two together, 4xy. And then always positive, the second term squared. So 16y squared. Or if you're more visual, you used one 4y here. You have 4y times 4y left. That's got to go on the end. Okay. And again, that x squared minus 4xy plus 16y squared, that part of the factor, this particular factor, is prime and will not factor any further. Okay. Problem number 6, 1331y to the 9th. Oh, yikes. Minus 216z to the 6th. I want to say 1331 is 11. The cube root of that is 11. But if I'm not sure, I know it's not a square. I'm going to do cube root second chevron, 1331. Yep, it's 11. So this would be 11 y to the 9th. The cube root of y to the 9th would be y to the 3rd times 11y to the 3rd times 11y to the 3rd. Because remember, we have to add the exponents. So y to the 3rd again is what would get me y to the 9th. Yep. 216, cube root of 216. Oh, nope. I want 3 second cube root. There we go. 216. 6. Okay, I was going to say 4. I'm glad I checked. So this will be 6z squared times 6z squared times 6z squared. Well, this is a nice one. All right. First root, 11y cubed. Second root, 6z squared. I want to keep the same sign, so that's going to be a minus. Now, ideally, if you're more visual, you can now cross these out, right? So squaring the first one, 11y to the 3rd, would leave me with 121y to the 6th. Multiply these together. But I need the opposite sign. So it's going to be a plus 66 y to the 3rd z squared. Always positive, 36 z to the 4th. Okay. There we go. Perfect. Perfect. Beautiful. I can check that if I want to by multiplying them together. It's going to take more time than I have, so I'm not going to today. Not going to right now anyway. All right. The second part of this is just factoring completely. Same types of problems. We're just adding a greatest common factor. So in problem number 7, you see a 2x to the cubed plus, or 2x cubed plus 54. It is a sum. There is a cube there, but the 2 in front is an issue. So I want to check and see if the 2 will factor out. And sure enough, 54 is even. So I can rewrite this as 2 times x cubed plus 27. Since I have that 2 out as a common factor, I'm just going to put that yellow line. That just helps me. You don't need to use that as a strategy, but if you forget that 2 in the end, it can cause a problem. I do recognize this x cubed as x times x times x, and that 27 is 3 times 3 times 3. So this is a sum of 2 cubes. I need the cube root of each. The cube root of x cubed is x. The cube root of 27 is 3. I'm going to keep the same operator as was in the original. And then the pattern is to square the first, use the opposite of what was in the original, the product of the 2 terms, and then always positive last term squared. 3 squared is 9. That 2 is going to come down. And this is it. As you can maybe see, it's a lot of remembering the pattern and actually utilizing that pattern more so than it is a bunch of manipulations, right? We're not doing a whole bunch of manipulating here. It is a lot of recognition. So problem number 8 is 2x to the 5th plus 2x squared. It is a sum. There are 2 terms. So this technically could be sum of the squares or the sum of the cubes. Since we're in the cube section, I'm going to go with cubes. But I'm going to pull out a 2, and I can also pull out an x squared. And that's going to leave me with x to the 3rd, 2x squared, take out 2x squared, leaves me with 1. Okay. Now I need to determine if I can factor x cubed plus 1. Well, x cubed is x times x times x, and 1 is 1 times 1 times 1. So to factor this, I will use the sum of 2 cubes. The cube root of x cubed is x. The cube root of 1 is 1. I keep the same sign as was in the original binomial. The second part is setting up the trinomial. And so I need the square of the first term, the opposite operator or sign, and then the product of the 2, and then always positive, the last one squared. 1 squared is 1. Bringing down what I factored out, I now have a list of all the factors together. Okay. All right, what else we got? Couple more and then an application. All right, I've got a negative 64 n to the 3rd x plus 8 n to the 3rd x. I got an m and an n. I've got a 64 and an 8. I can pull an x out for sure. I see that right away. M and n won't work. I can pull out an 8. And since I'm leading with a negative, I'm going to pull a negative. And that's going to give me 8m to the 3rd minus n to the 3rd. Okay, is this a perfect cube or is this a difference of 2 cubes? It's not a perfect square because cubes are not squares and 8 is not a perfect square. So it could be cubes. Is 8 is 2. So, this would be 2m times 2m times 2m. So that'll work. And n times n times n. Okay, so this first term is a perfect cube. The second term is a perfect cube. I'm good to go. I need the root, which is 2m of the first one, and the root of the second one, which is n. want to keep the same operator. I've used this guy. I've used this guy. So then I need a squared, or 4m squared. Opposite sign that was there. So plus the product of the two, 2mn. And then always positive on the last part of the trinomial, n squared. I'm going to bring down that minus 8x. And yeah, she's done. Okay. Problem number 10. I've got an 81r to the 4th s squared minus 24r s to the 5th. Oh, okay. So 81 and 24. 81 is not a perfect cube. So I can't do that. 24, not a perfect cube. But 81 and 24, and you may not know this, but 81 and 24 are both divisible by 3. That was kind of a hard get. So I can pull a 3 out. R to the 4th and r, I can pull an r out. S squared and s to the 5th, I can pull an s squared out. So greatest common factor is I can pull out a 3rs squared. And then I'm going to be left with 27 r to the 3rd minus 8 s to the 3rd. Okay. All right, we're in perfect cubes. 27 is a perfect cube. R third is a perfect cube. 8 is a perfect cube. S third is a perfect cube. So I'm going to be left here with 3r times 3r times 3r. And this is going to be 2s times 2s times 2s. All right. So as they're perfect cubes, I can use this particular pattern, take the root of the first term, 3r, and the root of the second term, which is 2s. I want to keep the same sign as the original. Then I need the trinomial piece. Since I've used a 3r here and a 2s there, in my trinomial, the first one is the square, or the remainder here, which is 9r squared. Opposite sign from what I started with. Product of the two, 6rs, always positive. Square of the last term, or if you're more visual, you can multiply those two together, 4s squared. I'm going to bring down the 3rs squared because it is also one of my factors. And then I'm going to put it together. There. These were a lot of minuses, but that's okay. The pluses are just the same, right? It's the same pattern. Keep it the same. Always the opposite on the second sign, and the third sign there is always positive. Okay. All right, last one I have here is an application. It says, over time, a 12-inch cube of ice melts to a cube of ice of side length x. Write a polynomial that represents the volume of ice that melted away. Then rewrite that polynomial to factored form. Oh, it's kind of like what we did in the last one, huh? We did one of these in the last one. Okay, so the idea here is that this is going to be a cube of side x. Right? And, oh no, it's 12. This is the 12-inch cube. Okay, 12, 12, 12. And it's going to melt away to be x. Oh, okay. So they want us to find all of this melty stuff. Oh, I can't spell. Volume. Okay, so how do we find the melted volume? Well, it's the difference between the two cubes. So it is going to be the volume of the big cube minus the volume of the small cube. VOLUME. So that would be the missing volume, right? If you take what was in the big cube and you subtract away the volume of the small cube, then the puddle on the floor is what's missing off of the big cube. Yeah? Okay. So the big cube is length times width times height, or 12 cubed, minus the volume of the small cube, which is x times x times x, or x cubed. So the volume that's missing would be 12 cubed minus x cubed. Does 12 cubed have a cube root? because this is it for the polynomial. I should figure out 12 cubed if I wanted. 12 cubed is 1728. I knew that. Right? But then they say to rewrite this polynomial in factored form. Well, I know that 1728 is 12 cubed. So, and this is x cubed. So this is the difference of two squares. This is what we've been doing. The first term is 12 times 12 times 12. The second term is x times x times x. So when I factor it, it will be that root of 12 and the root of x. I want the same sign as was in the original expression or equation. Then it's the square of the first one, 144, the opposite sign from where I started, the product of the two together. Always add the square of the last. So this is the polynomial in factored form, and this is the polynomial. So that's the poly, and that's factored. And I've got both answers. All right. I hope you will join us next time for the next section where we put all of these together and we have to do a grab bag. So next time we're going to talk about strategies when you're just looking at a polynomial and you don't know much about it. You're asked to factor. So we'll go over all of those next time. In the meantime, if you need anything, please don't hesitate to reach out to me or to pop into the Math Center and ask Julia or any of the multitudes of people that help her there. They will be glad to walk through some of these with you, answer any questions. All right. Thank you. See you next time.